But the reason I chose them is they're all based on real world information. We're going to be doing work, and you're going to have to deal with high frequency stuff and the actual connectivity. So you're going to have cabling and stuff like this. You got to figure out if the cable is going to operate the way you think it is at the frequency. And it can be nightmarish at times to figure this out, especially when you get cables behind walls and you don't know how long they are. Then you have to put a ding on one end and see how long it takes to get to the other to figure it out. The time delay is the length divided by the speed of light.
Determine the resistance, internal inductance, external inductance,
R internal and L external, go ahead.
and capacitance of a typical ribbon cable consisting of two 28 AWG 7x36 wires, 2 meters in length and separated by 50 mils at 100 megahertz.
So this is 36 gauge wire, and there are 7 of them.
What's the point of putting the 28 there if you get all the information?
Because 28 would be a solid wire. What they're saying is, if you have a conduit pipe that would fit one 28 gauge wire or a whole bunch of 28 gauge, you can say this is going to have the same cross-sectional area. And there, a lot of this stuff, by the way, this is all standard stuff. Gauge is an old English measure. You know how gauge came about? Back in the day of you have cannonballs. So you would put something of a certain diameter, and how many balls you could fit in there snugly, that would be gauge. Like, if you think about this, somebody know what a shotgun is. All right, 12 gauge, 12 balls fit in there. What about 16 gauge, 16, 20 gauge? And the gauge, as the gauge gets bigger, the actual size or diameter goes down. That's where gauge
goes down.
20 gauge shotgun has a barrel that's much thinner, or I should say a smaller circumference than 12 gauge.
So how would it fit more balls?
There's a circle where gauge is measured. 12 gauge, you could fit 12 tightly, like stuck balls. Follow me on this?
Okay.
No spacing. They're snug. They're circles. There's a formula for this.
Yeah.
8 gauge would be 8. Now the diameter of this thing, I don't remember, but you can actually calculate it. You can do an inverse calculation. But that's where the gauge came in. And that's the same with wire gauge. Now that's not the same measurement. The gauge for that has a different standard than it does for rifles. Okay, here's the thing. Think of it this way. You're going to have one wire, and this wire is made of by 7 by 36 gauge wires. Then you're going to have another one. Current's going to flow down this way and then flow this way. It's differentially driven. It says 2 wires, right? 2 wires, yeah. It's used to connect things for like a communication. Like current goes down one, back the other. Think of Cat5 cabling, if you will, but it's not a really good example, but this is what they're talking about. The first thing we're going to do is get the resistance of this. To get the resistance, you have to look at the smallest wire, which is 36 gauge. So if you look in there for 36 gauge wire, what is the diameter in mils? Just look up 36 gauge wire.
Oh, for a single
One wire, that's
Gotcha.
it. They're
So
all in
solid.
parallel. You look at the smallest wire because there's 7 in parallel. So this is 5 mils. That's the diameter. Now, what is that in terms of meters? It's 5 times 2.5 times 10 to the minus 5th meters. Isn't that right, the conversion? That's the diameter. Then divide this by 2. So that way we can get the radius. So this is the radius in meters of a 36 gauge wire. 6.4 times 10 to the minus 5, and that's meters. The next thing you do is find the skin depth. All right, now how do you get the skin depth? It's copper wire, right? All right, so it's 1 over square root of pi 10 to the 8, and mu relative is 1 for copper. It would be 1,000 for 1045 still, so it's just 1. Then it's times mu naught, which is 4 pi times 10 to the minus 7th, right? Okay, so what is that? 6.6 micrometers. And so you can conclude that the skin depth is much less than the radius A. So that means for a single wire that is 2 meters long, we're going to have 2 of them. When we calculate the AC resistance of this, we should get a length, which is 2, and then it would be divided by sigma, and I'll put sigma first, which is 5.8 times 10 to the 7th, and it would be 1 over ohm meters, or Siemens per meter. So now this is going to be equal to sigma times the circumferential area, or the area the AC current would flow through, and that will be 2 pi A times the skin depth. So what is RAC for a simple 2 meter long strand? So this is 12.99 ohms. The next thing I'm going to do is just calculate the resistance of this group of wires. For one of these wires 2 meters long, it's that. Therefore, the resistance for just L equals 2 meters would be that divided by the number, which is 7. So it would be, I call it 13 divided by 7, because they're all in parallel. You got 7 wires in parallel, 36 gauge. One 36 gauge wire has this many ohms, 12.99. If we put a bunch in parallel, we divide by the number, that's 7. Current goes down and comes back. Total AC resistance, R, is equal to this times 2. So it's roughly 26 over 7. Can you tell me what that is? 3.74 ohms. Now we're going to do the inductance just for a single wire, but this is going to be the internal. We'll do external after. The length of this wire is going to be 2 meters. And this is going to be high frequency, or LAC. We start by saying find LDC. Well, the mu relative of this one is 1. So the DC resistance is mu 0 over 8 pi. And that is per meter. Now I multiply that by 2 times the skin depth over the radius A. And that would be per meter. Then I have to multiply it by 2 because it's got 2 meters in length. This is just for the upper portion for one single wire of 2 meters in length. So that will be the inductance. And tell me what it is. 20.65 times 10 to the minus 9 for a single wire, 2 meters long. Now that's for one wire, but there are 7 of them. So I'm going to say L total. Now this is internal too, would be equal to L divided by 7, because they're all in parallel. Those are parallel inductances. But then I have to multiply it by 2 because current's going to go down and back. I get an internal inductance of 5.9 times 10 to the minus 9. I'm not going to ask this. They ask for the capacitance and they ask for the inductance. That's all the internal stuff we can get. We can get inductance and we can get resistance. Now we're going to talk about the external inductance and external capacitance. They have to give the separation distance between these two wires. Now you're going to assume you have, and these are going to be 28 gauge wires. And we need the radius A of 28 gauge. It should be 28 gauge stranded, but this radius should be almost the same. Or the diameters, either one. They'll be in mils, but give me a second. Now you got a spacing, center to center spacing here, and I'll call it S. Each one of these larger wires is going to have a radius, and I'll call it A prime. That's going to be the radius of these wires. I don't know if you remember how to calculate the mutual inductance of wires, but what you normally do, first we assume they're infinitely long, then you calculate the H field from one. And the H field from one would be I over 2 pi rho, where rho would be the distance from the center to that point. Then once you have that, you integrate from the radius here to find the total flux. And then you multiply that by 2 because there's 2 wires and those fluxes added. Current flowing down this way, flux out of the board. Current flowing down this way, flux out of the board. The flux is additive. Now you find out that the external inductance is going to be the length 2. And then it's going to be, do you remember that the H field itself is I over 2 pi rho A field. From a straight wire, if you just had a straight wire with a current I and I'm a distance rho away, the H field here would be proportional to I over 2 pi rho, because that's the circumferential distance, would be the A phi direction. Then if you multiply that by mu, you get this, right? That would be the B field. Now, when you integrate that over the surface area, you get a natural log of the outer radius over the inner radius, because it's a 1 over r. You're going to have the mu, you're going to be divided by 2 pi. The inductance, we divide out I, but there's 2 of them. So you get it's 2 times mu 0 over pi, the natural log. See, it's going to be separation distance minus 2a, so it's going to be S minus 2a over A. And that's going to be the external inductance. You don't remember?
I did up until you started saying that.
Well, you agree, if we have a current I, just look at one wire at a time. If I'm up at a distance rho away, I have an H field equal to I over 2 pi rho in the A phi direction. The B field is what you want, so you multiply it by mu 0. Now I have the B field. To get the total flux, the magnetic flux, only from the first wire, it's going to be an integral from 0 to 2. Integral, you're going to have the B field, right? Normally it's B dot ds. Well, the B field is mu 0 I over 2 pi rho. It's in the A phi direction. Then you have to dot it with the differential surface area right here. And that's in the plane connecting the 2 wires. So that differential surface here is going to be in the A phi direction. Has to be perpendicular to that. and it's going to be d rho dz. dz goes, this would be z goes from 0 to that. If you look at this, you don't start here because that's the internal inductance we calculated. You go from here to here. So if you go from here to here, you're going to go from A, and then it's going to be S minus 2A, because I'm assuming you don't integrate into this wire. You go from right here, so start at A, and then you go right to that point. That would be S minus A. Or sorry, that's S minus, not 2A, S minus A, my bad. So that's for 1. That's the flux from 1. If you get the flux from the top one, it's twice this. And then if you divide by I, this cancels, 2's cancel, you get mu 0 over pi. Then you do the dz integration, you're going to get a 2 here, natural log here, because here you got the rho, so if you integrate d rho over rho, you get natural log, so you get natural log of, and it's really going to be S minus A over A, and that will be get rid of that 2A, sorry. S minus A over A. Usually S is much, much greater than A, so you can ignore that a lot of times. But if you do this, now what is the radius of 28 gauge stranded wire?
7 by 36 is 15 its diameter.
So divide by 2, so the radius would be 15 by 2, and then it's times what? 2.5 times 10 to the minus 5. So that would be what? In meters. Can you tell me what that is?
1.875, 10 to the negative 1.
So what do you get for this?
You got 1.53 times 10 to the negative 6.
Now, how do you get the capacitance? This is external capacitance. We're assuming region between these two braided wires is air. If it is air, when you send a current down this way and a current's returning this way, the electric fields will be perpendicular to the direction of current flow. And the magnetic fields will be perpendicular to the electric field, and there will be no component of the magnetic field in the direction of current. It's not like a wave gun. That means you can use this clever little equation, and it saves you so much time. If you want to know, now this is only per meter. So if you take mu between the region times epsilon between the region, it will be equal to L times C, where L is going to be the inductance between the region times C. Mu and epsilon are constants. And if it's just air, it's mu naught epsilon naught. So I have mu naught epsilon naught, and you know the square root of that is 1 over c. So that itself is 1 over c squared. So which is 1 over c squared equal to L. But that's L per meter. This is what L per meter would be. This is L external per meter. So if you take that answer that we got and divide it by 2, that would be the L per meter. This is the answer we got for 2 meters, right? Divide by 2, now you get per meter. It's 1.53 by 2 times 10 to the minus 6, that's L, times C. So you can get C, this is capacitance. You can take the capacitance itself is going to be equal to 1 over 3 times 10 to the 8th squared, that's c squared. And then it's going to be equal to, I have to go ahead and divide everything by this, so it's going to be on top you get a 2, and on the bottom you get 1.53 times 10 to the minus 6. Tell me what that is.
You got 14.5
picofarad. That is per meter. Now multiply by the length. But you have to do this calculation of per meter. You can't do it with the total length here for L. Multiply that by 2, it's going to be, what, 29 picofarad? So remember, this calculation is per meter. Once you have the per meter, you multiply it by the total length of the 2 cables. I mean, remember, it's differential mode. Current goes down one, back the other. The total length, it's basically the length of that segment, which is 2 meters. Did they ask for anything else?
Characteristic impedance.
All right, this is 4.5 picofarads per meter. That's the only capacitance. Now let's take a look at the inductance. The inductance here, that's external. Yeah, 1.53 microhenries. What was the internal inductance?
5.95 nanometers.
So do you realize the internal is so much less than the external? You don't need to consider it for the characteristic impedance. So what is characteristic impedance always? It's the square root of L over C. Back in the day of transmission lines, L external over C external, and the C external, C total external is going to be 29 picofarads. So just tell me what that is.
229.
This calculation is from EMAG 1, so you're probably a little rusty with that. So what might be on the quiz? Why don't we talk about a resistor? Remember what a resistor looks like? That looks like a resistor for starters. Then it has ye old capacitance that's a parasite. And then it has an inductor here, and it's called the lead inductance. What you really want is the impedance between these 2 points. So you'd like to know what Zn is here. What you normally get here is something that's in dB. And it's either 20 times the log base 10 of R, or it's just, they'll show you log of R, and they don't have a value here of like 4,700 ohms. They're telling you that's where that point is. A resistor at low frequency always looks like a resistor. Now this is going to be a logarithmic scale, log of f, but it'll be actually shown like, and this would be like 10, 100, 1,000, where there'll be decades. Each decade of difference has the same measurement on the horizontal axis. So go over here. This is the low frequency cutoff. And if you remember, what is that? That's 1 over 2 pi R times C. That's C parasitic. Then it starts going down by minus 20 dB until it hits self-resonant frequency. And that's 1 over 2 pi square root of LC, right? Then it starts going up at 20 dB. That's the resistance. If you want, you can get it by just writing the equation for this. You could say it's really, I'll call it J omega L plus, and then you got these two in parallel, so it's plus 1 over R plus J omega C. And you can go ahead and you can figure out where the pole zeros are. Instead of omega, you put in 2 pi F. And you can do that. I'm just showing you that's the result, period. What happens if you have an inductor? Really, an inductor, an ideal inductor, looks like 0 ohms or short circuit at DC. It's just wire, and if wire is infinite conductivity. But really with an inductor, if you do this Bode plot, and you plot log F here, there's only one frequency you worry about. That is the self-resonant frequency. And that's equal to, and they're always the same for all of them, 2 pi square root of LC. You know the value of L, you can calculate the value of C. This is minus 20 dB, this would be plus 20 dB, and this would be a logarithmic scale, log, of the magnitude of Z. You could put a 20 in there. If the axis was dB, it would have a 20 in front of that. If the axis is just like 4,700 or something, then it doesn't have the 20. That's the inductor. What about the capacitor? Inverse to this. The capacitor looks like this. And I can write the equation for you, but if you did the homework, you know it, it's pretty straightforward. The capacitor looks like this. It's still going to have the resonant frequency, but it's going to come in at minus 20 dB per decade. And then it's going to go up at plus 20 dB per decade. And the self-resonance will be the same. And that would be a capacitor. I'm not going to do anything tricky where, what about an electrolytic capacitor where there's bleed resistance you have to worry about? And I'm not going to do anything that's screwy. It's basically the simplest model of components that are used widely. Are there any questions?
Question 1, 5.4.1, they give you the graph, but how do you find ZP? How do you find
Okay.
a possible impedance expression?
Why don't we do it? Many ways to do this. Normally when you look at this, you write an equation, put the poles and the zeros in their appropriate spot. And then you always start with a constant. So I'm going to say Z of S. And remember, S is equal to sigma plus J omega. We'll make sigma 0. You always start with the constant K. You don't know what that K is. We can get it. Anytime it starts going down at 20 dB per decade, that is a pole. And that pole is as F1. So it's going to be this divided by the pole, so it's going to be S plus 1, because S and omega have the same magnitude. The next one, it flattens out. Where does it flatten out? At 3, right? So then you put S plus 3. This thing's going up at 20 dB per decade. This is going down at 20 dB. It flattens out. Then it starts going down again at 10, right? So you divide again by S plus 10. My bad, I'm assuming it's doing this. What I should have done is just put S there. That's absolutely true, my bad. He's assuming it's this. You can get the actual plot the way I did it, but the problem is it'll be cutting in right there, and it won't be continually going down. It's assumed to be straight like that, going down 20 dB. You want all the coefficients of this to be 1. So I'm going to take K, and now I'm factoring out of 3. When I factor out that 3, now I have S over 3 plus 1. Then downstairs, leave the S alone. And here, I'm going to have S over 10 plus 1 and a factor of 10 out here. The whole idea is this. Anytime you have a pole or a 0, when you have S plus 1, this is approximately equal to just 1 if S is less than 1. That's the way a Bode plot works. And if S is greater than 1, then this thing really looks like S. In other words, the pole kicks in. By the same token, if you have S over A plus 1, then this thing looks as one as long as S over A is less than 1. Remember, if this is less than 1, call it J omega. If J omega over A is less than 1, the magnitude of this is something less than 1 squared plus 1 square root. That's approximately 1. So that's 1. And if S over A is greater than 1, it looks like this. See this? If you're down here, this 0 and that pole are not on. So if you look at this, I can say this whole thing right here is equal to the value of minus 12 dB. Minus 12 dB, we're going to do the conversion, is associated with K times 3 over 10, and the S value there is 1, omega is 1, so it's 3/10. That's 12 minus 12 dB. So what is 12 minus 12 dB? It's 10 to the what? Minus 1.2 is equal to K times 3/10. Remember, all this stuff, this is effectively 1, this is effectively 1. What do I have out in front? I have K times 3 over 10S, but at the S value here would be 1. What is K then? K equals 10 thirds times 10 to the minus 1.2, and what do you get for K? 0.8. So this should be